Alright, time for another draft physics video presentation. We're going to go over photons again and Feynman and a whole perspective on what the science is, or physics. I guess they would apply their theory to all the sciences, and we should go back to voodoo, because it worked. Mysticism's, medicine men. We won't try to figure out why something works. We'll just learn how to do recipes. And, it's, I think, terribly unscientific. I think Feynman was a horrible physicist and a horrible scientist in the sense that he's, um, broke the whole process by essentially arguing that it is just magic and we ought to just leave it at that. We live in a magic verse, and let's just figure out how to exploit the magic verse and not bother with this figuring it out, because that's almost offending the magic verse. It really is just such religion. So anyway, so the argument about photons, there's a certain number of facts, things, details we know about photons. So they have this property of a frequency. Now, everybody wants to turn that into a wavelength. So everything has to be understood. Everything has a frequency. We are forced or obliged in some way to think of it as some sort of, mechanism that has something to do with some continuous string or line or mechanism of whatever. A continuous thing that has lumps in it. Okay, so, like that we have to have a spaghetti universe. And then they put a second field on that and make it into a double helix for whatever reason, blah, blah, blah. And a frequency is just, it can be understood as just events. A clock has mechanisms in it that duplicate, or create the frequency, and you can just see them. They go this way, and they go that way, and they go this way, and they go that way, and they're not waving. They're hitting something. They're jamming something, they're stopping something, they're reciprocating, causing a pattern, and it doesn't have any waves in it. And so frequencies can exist without having wavelengths. You can think of it as a wavelength. You can imagine it as a, how, that the time between some event is something to do with some spring or some string or some other thing, but it just is totally just isn't necessary to understand that it's a sequence of events. And the other thing a photon has, they know, is polarization, so it has a size. And this is what just, you can just logically go through some of this stuff and figure out, well, if the size is, 1,000 atoms of distance, then it's not likely that one single little electron sitting inside of an atom is somehow creating this thing, okay, that this wave that somehow goes out, much bigger than it is. How can it create something that takes up so much space? The idea that it's a little particle or a little bit or a place in the universe that's waving, that somehow is creating waves. Well, why would the wave get to a certain size and that's it? If it's a wave, how does it stop expanding? How does it stop getting bigger? It has one standard polarization for, what the light is. I mean, what it does. You can't deny these are its properties. These are the things it has. So red light, when red light hits a surface, it's different than blue light, in the sense that whatever the photon is, the thing we're going to call a photon, the red light is going to do, is going to hit a surface area because of its polarization. It's going to affect a size of space, and that blue light, okay, is going to affect, half that amount of space. And then if I go, if I go higher and higher, I get narrower and narrower. Okay, so an X-ray would be a little thin line, and a radio wave would be this big giant thing. So there's clearly a proportional relationship between the frequency, that how often one of these clumps happen, and how much the clumps are out of alignment in terms of how much space they're moving through. And so you kind of know that a photon has to have a kind of a shape. It's not just something we call a photon and just say that's all we're going to say about it. And I would argue that you could think of it as like an envelope, and you could just think about the bits of the photon are just on the envelope. The photon has no dimension in one direction, no discernible amount of dimension. Very thin, but it's got a definite tallness, and it's got a length. It's just a fact. There's a certain amount of time it takes. You have to have, again, it's just this idea of what's a wave? Is a wave this? Does that have a frequency? Does that tell you anything? You have to have more than one of them. And there's every indication that that's a truth about a photon, that even if you want to think about waves, you got to think about it as you got to have a certain amount of it, or it's not going to be understood. It's not going to be received. And when we receive other kinds of photons like radio waves, we do sample the signal. We sample a certain amount of time to say, okay, this is 500 megahertz. It's not just one blob, one blip, one lump, and we say, oh, we know what it is. And that's sort of a giveaway, that this is an event, a photon. It's not just a blob traveling through space. There's no such thing as a photon. Photon. No, the photon is made of it's a composite object. It's more than one event, that takes place. And again, its polarization is a real thing. And there's a proportional relationship between the size of the polarization and the wavelength of the light. So there's lots of mechanisms. Now you've got to figure out, well, how's it being created then? And I made a simple argument that one of the things we know is that the atom is causing an electron to move some distance. It's moving from some location to another location, and does that movement quickly. So the idea would be is I could capture a lot of energy by moving this chalk quickly. If I could move it quickly enough, it would capture all the energy between it and the new location and essentially compress it into a smaller amount of space. So as the electron would move, it's moving into a field, and whatever that field is, it's moving the speed of light. These little bits of cell phones and all kinds of stuff, it moves through it, it pushes it, it collects it, and so it takes stuff that was occupying this much space, and it will compress it into this much space. And you could sort of understand that could look like a frequency of compression, where you've taken energy and taken what there was, the light, and you've put it into a smaller package of time. And then it's less stuff, and then there's going to be more stuff again, and that ends up making a frequency. And that could be understood as being part of what's creating a photon. But again, the polarization just kind of screams at you that it's got to be more than one electron that's creating the process. That there's a sequence of events that takes place, this atom, and then this atom, and then this atom does it, where each does it in sequence, and that's what's creating the photon. And the sequence has to be created by, again, some sort of physical structure, and you can start theorizing about how electricity might provoke the creation of photons, that maybe the energy is it starts in here in the center of, say, a conductor. So if you're looking into a conductor, and it might start in the center and work its way out to the outside, you could sort of understand that would allow it to affect an atom, and then affect another atom, and then affect another atom. And because they're moving in the direction of the signal, that would create the distance between them, and their polarization would be commensurate to that, because there'd be so much possible out of alignment in just moving through the atoms, and then you have to figure that that also has something to do with why there's the different colors or the different subtle changes in the frequency would be dependent on what atoms it's transferring through. Different atoms will, are of different size, and it would take different amount of time to transfer energy from one atom to the next atom to the next atom, depending on how the atoms are shaped and sized. And all that could be understood as plausible and realistic explanations. And we don't have to believe there's, just some magical thing that some wave exists in space, and then all of a sudden the wave decides for no good reason to go this way, or it does this way, or it's doing this, and I don't know, it's going to all these locations and then decides to go to this location instead, or whatever. I mean, it's to give up on the fact that there's a physical explanation, and we can already see these properties. I mean, they're saying I have properties. So we could use examples like a piece of glass, and there's 40% the light will change its speed, so to speak. Light goes in at a certain speed, and there'll be a delay in it coming out the other side of the glass, and that you can change that. You can add a little tiny particles of lead or some other material, and you'll actually change how long it takes the light to travel through the glass, and you'll change how it reflects and deflects. And so there's a physical process here. It's not some random thing that's saying how much light reflects. Well, if I put different materials in the glass, I can change how much light reflects. I can change how much, what this angle will be of, how much the light will deflect. And, I can change all this by just changing the chemistry. Why should I think it's random? Why should I think it's just some little random God decides to tell it what to do? It seems quite obvious that the matter is telling it what to do. The circumstances of the condition of the electrons and protons are saying whether it's going to be transparent at all and whether it's going to reflect light at all. And again, the percentage arguments gets back to understanding this, things like the two-slit experiment, and understanding that whenever light's interacting with a surface, whenever it's interacting with something, it's a pattern. It's a pattern, a sequence of events, stuff in a spatial pattern that's going into the thing, and that pattern can be broken, that you can send one piece this way, and this piece could end up going that way, and this piece could end up going straight. And you could have the same thing happening on these other surfaces where pieces of this pattern are going through the same obstacle course at different times and in different places, and that would be plenty of places where you could just end up putting the pattern back together, and that's all it is. It's a simple pattern going in, it's a simple pattern coming out, and you can make it by breaking it and just remaking it, because it is so simple. It's just a frequency with a little bit of an alignment issue, and this shouldn't be all that challenging. You sort of understand too that there's lots of, well, what about? You can go, what about forever, almost, in terms of finding all the conditions. But you could argue that if I sent a bunch of red light into a slit pattern and I was breaking and making the pattern, why can't I remake an ultraviolet light? That is, have the pattern get all close together because I send pieces and they change red light into blue light. Well, maybe that is possible, but the problem is the red light has this really big polarization, and the blue light has a much smaller polarization, and that's the part you're not likely to do. You're not likely to be able to take parts and scatter them and make them land in a smaller location. It's more likely that you end up making them land on a wider location, and so you would break the rules that blue light can only be seen as blue light because not only because it has the right frequency, but because it does hit a small amount of surface. But anyway, so I mean, there's all kinds of ways it can be thought about, but all of the facts already there, and it's just putting them together. The theory of evolution had problems, and people figured it out. It was, why aren't there any missing links, right? I mean, you're saying, we should be able to find, fossils of all of our little ancestors, in all their different little conditions, that whole evolutionary scale picture kind of idea. And, it was a real argument. You could say, well, why aren't there missing links? Why don't I have a complete record? Why can't I find the bones of all of our ancestors? And the simple answer was, well, first, evolution has conditions, and it works a certain way. And it's based on mutation. And clearly, big, successful populations aren't the ones that are likely to evolve. Because if there is any new character who pops up that does something different, he's going to get diluted by the DNA of all these other characters. And now it's just going to dilute his DNA, and he's not going to... So big herds don't do any evolving, not much. And what really happens is a couple of individuals scatter off of the big herd, and they do a bunch of inbreeding, okay, and a bunch of breeding not in a big giant population. So any individual that comes out weird or different, he has a much higher likelihood of his DNA surviving. And so that's where the evolution happens in very tiny populations. So we get lots of fossils from these guys, and we don't get too many fossils from these guys because they're 1 in a million who are in that little tiny evolving tribe. And then when this tribe gets very successful and it gets very big, then it takes over, okay? And then that's why we have these huge jumps in the evolution, is because it's not until it almost changes into a new species that it has a chance to overcome the existing population and do the evolutionary thing of destroying your competition, taking their place and succeeding. So, I mean, it has two elements to it. It has the idea that inbreeding creates more mutations, more brokenness, more errors, and the whole system runs on errors. So you're making more errors. You're doing more experiments where change is likely, and you're a small population. So a couple of good reasons why there are. So I don't want to do a biology lesson, but it can be understood that there's facts and there's reasoning, and you can explain it, and you can find out why. And finding out why is the beautiful thing of science. Understanding the truth, understanding how it really works, is the thing that has real value, which makes us mean something. I mean, walking around thinking because the, astrologer, and the medicine man are the same person, and they, having a false notion of why the little magic bag has stuff in it that'll make you feel better, because it's magic, or because you understand that, I'm made of chemistry, and that certain chemicals can, augment my chemistry and help fix a problem. Having the right answer is so important. It's got such meaning, and just being able to manipulate the world with a bunch of false notions and fake ideas. That's embarrassing. It's not the right stuff. I mean, that's not what lands you on the moon. I just think it's a terrible attitude that Feynman had, and what Feynman represents. And yes, likable guy, witty, all that kind of crap as a human being. I don't have anything against him. But I think as a scientist, he failed dismally. And they call him this great teacher, somebody who's just teaching people how to give up, to quit using their brain. Just be part of the Borg. Join our religion of little fables.
To make these arguments. It's useless. It doesn't add anything. And so we're not going to make my imaginary mind.
Yeah, so we're not going to try to get the right answer. So again, you could argue that religious people were trying to get the right answer 2,000 years ago. They were after the truth. Okay, they weren't after a lie. They didn't want a lie. Okay, but they were just going with, well, what's the best theory they could figure out? Because they didn't have a record. They didn't know the planet was 4 billion years old. They didn't understand how the frickin' rest of the universe was working. They didn't even understand they were revolving around the sun. So yeah, they drew lots of wrong conclusions, and they probably shouldn't have been drawing any conclusions. They should have just been collecting data as honestly as possible without going too far into speculating. But yeah, it became impossible as a thought experiment. It's very difficult to figure out why anything exists. But clearly, their answers didn't get to any core. I mean, this idea of gods and their soap opera just changes where you're asking the question, because then you still have to ask the question, well, where did the gods come from? And did they evolve on some other planet? I mean, it just doesn't it doesn't get you anywhere. It doesn't go anywhere as an answer. It's so underdone. And it's these underdone answers that people settle for that it's embarrassing. It's embarrassing the human intelligence to sit there and settle for such incomplete answers. And to say, well, that's good enough. We'll just stay there. We'll just stay ignorant.
Arguments about the various gods that make the numbers. And so I'm left, if I'm a modern scientist, with a description of the situation.
Yeah, so find that the thing you're trying to describe and recognize its properties. So, I mean, they had full knowledge in Feynman's day that light was polarized. They had every reason to believe the polarization was a substantial amount of distance, and so why did they sit there and even contemplate some idea that a single electron could possibly create a photon? How could it possibly create this object that has a standard size, from such a tiny location? How does it little tiny jiggle of an electron, a little movement of an electron, create something so large? It's not possible. So they should have been looking for a better answer.
Right. Now I prepared the audience. Used up all my time to prepare the audience. Doesn't make any difference. I will continue anyway, in spite of it.
So he just spent the first 30 minutes of the video basically saying, look, my students don't understand it. I don't understand it. We don't have to understand it. Don't worry about understanding. Understanding is a silly word anyway. Forget about it. The Mayans didn't understand, and that everything worked out fine because they had a system, and all you need is a system for figuring out when it's going to happen, and that's all that's important. You don't need to know why it's happening. Just terrible.
In fact, I used up all the time, to describe the theory. And in describing it, I will first describe some part of it. The theory is the properties of light, electrons, and the interaction of light and electrons.
Yeah, well, it's the only thing that there is, really. I mean, we know it seems pretty likely that photons must interact with protons now and then. So it's not just about electrons. But clearly, whatever protons are doing, it isn't obvious, you could argue. Now, protons might be where are causing reflections, I would argue. And, electrons are causing the transmission. But they haven't even considered that part of the theory, because the electrons are clearly photons are made of energy that more substantially affects an electron. So I would argue the answer is that yes, it's the energy that repels electrons that photons are made out of, and that's why they're so specific to electrons, but whatever.
It's all one theory. I've cut it into 3 parts that way. And the first thing I'm going to start with is the properties of light. Okay? I'm going to tell you some of the properties of light, and I hope, if I can do it, to get to the key.
See, now, the properties of light, you have to separate when you're talking about the properties of something, and then you talk about the symptoms. So, you're trying to dissect what the disease is, whether it's a virus or a microbe. So you see what it does. Does it cause a fever? Does it do this? Does it do that? And you can put it into classifications because of what it does. All right, so we know what photons do, and that's how we figure out that it's polarized. We put it through filters, and we can figure out that it has this effect. And then we take the effect and then draw a picture of what a possible cause of the effect could be. And so there is a difference between describing the properties of a photon and then describing experiments that indicate what a photon might be. The two things are kind of different, and so Feynman won't sit there and dissect what a photon is in the sense of what we understand a photon must be. So a photon has to be something that travels through space, and it does so with a polarization, with a size, and it has to do so with a length. And these aren't the things he's going to talk about. That it's not a thing that just lands and does something. It has to do more than just affect one electron. I mean, like I said, this is their biggest and most catastrophic mistake, is not to understand that you're not forcing the photon to be human or a platypus or some, you're trying to say, what is it? And one of the features it is something at a frequency. And that a frequency is innately not something that just has this. That's a thing, a blob. That's not a frequency. And so you have to understand that, yes, a photon's got to be more complicated than this. It's not just a fist.
Point, and then we'll continue in the following lectures to elaborate on it. First, I don't go through the history of the theory of light. It had various things. The first and most important thing I would say is that Newton found out that what we see as white light is a mixture of otherwise pure stuff that's easy to understand. If you understand how each of the parts works, you just put the mixture back together again.
Right, so we know the key feature. I mean, I didn't really say that, but I mean, obviously we know that photons come in this range of a huge range in frequency. So we know that a distinguishing feature is frequency. Now, yeah, Newton broke it down into color, but he didn't know what he was breaking it down to was into groups of frequencies or a class of frequency. But that there was other light that we couldn't see that's at all these other frequencies. So yeah, it's one of the properties of light is that it carries a frequency, and it's just there's no sense in saying frequency doesn't require frequency, that somehow you don't have to have the event doesn't have to happen over a period of time with sub-events in it, and you can still have a frequency, that I can just show up with one wave, throw it at you, and therefore you know what frequency it is.
And then you separate the light in the prism, which is done automatically in Auckland very often, as far as I can tell, in rainbows. And the various colored, if you would separate light in the prism and take out the part that looked, say, yellow, then you couldn't separate that any further in another prism. It just stayed yellow. That's called monochromatic light, light of one color.
Right, so it's just light of a frequency, and it's a range of frequencies.
I'm going to discuss all my phenomena for a while with light of one color because it's simpler. The first thing, Newton believed that light was a corpuscular thing and turned out to have very strange properties from that point of view.
Right, so the idea of thinking about it being corpuscular has to be in that context of understanding it has a frequency. Now, Newton didn't know it had a frequency. So when he started off thinking about it being corpuscular, he's saying that the event of a photon is an event. So that part was correct, but it's an event that has more than one event in it. So I guess, you can understand why Newton knew, or why Newton wasn't positing some idea that a photon was a composite object, because obviously it's a recognition of a pattern. We can say that it's a pattern. There's plenty of information saying why we should conclude it's a pattern. There's no reason for Newton to think about it being a composite pattern. He's just thinking of it as being something that is clearly recognizable as a distinction between red and yellow. But there's no, it's always bad that they always just do this. This is almost like in politics where you have to be a draconian self-obsessed, selfish, capitalist, greedy scumbag, or you have to be some loopy liberal. Why are these our only two choices? Clump, billiard ball, or ocean wave, and it's very unproductive to be forced to argue either one of those sides as exclusively and narrowly defined. I can't be anything else. It can't be anything else.
And it was then explained that many of these strange properties was because, in fact, it was a wave, which was wrong. It turned out he was right. It was a particle.
So let's understand, this is, people who are wave believers will cite Feynman, all kinds of stuff, and it just seems kind of ironic that, he overtly now, this is his second time he's made the point, but I mean, he's making the point very aggressively that it's not a wave. Because, but he doesn't believe it's a particle either, in the sense that he believes the universe is telling things where to go by some magical mechanism, not some mechanical one that would have something to do with discrete objects interacting in discrete ways. His whole foundation of his science is sort of dependent on this understanding of an interaction between an electron and proton, a photon, and yet he doesn't think that interaction is mechanical.
It is corpuscular. The reason that he said it was corpuscular was based on an incorrect guess as to the behavior of waves, and his argument was wrong, logically. But it turned out in the end that it was particles. Now, how I talk about how I know it's particles is this. If we make an
So I don't want to, I've done the same exact video before where I've played this part of Feynman, but I have a better capacity to argue it because I have more definition in terms of what I've been able to discern a photon is. So I can better explain why they overlook those details. So, Newton's argument is the shadow argument fundamentally, and, that waves would fill in more of the shadow, and, particles would be more likely to create a hard shadow. And clearly the shadow is a little bit mushy, so there is some hope for waves. If you're the high enough frequency, would be the argument that the waves don't fill in as much when the frequency is higher, blah, 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 blah. But it's really doesn't, there's lots of other effects to put into the pool of effects that you're going to have to explain. And that's part of where the physics fails, is they just point out in one way that where there's a problem and use that one thing and just ignore all the other evidence pointing to the fact that that can't be the right answer. Just like they ignore that water waves don't produce interference patterns, and light does in single slits.
Instrument to detect light that's as sensitive as it can possibly be made. We make it more and more sensitive. In fact, this thing is called a photomultiplier. And that's not the only instrument. I just take one for an example. It doesn't make any difference how we do it. When we get to light that's sufficiently weak, an instrument to detect it hears clicks, pulses, as if it was rain falling on something. You can bang, 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 bang. When the light is bright, the rain goes bang, 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 a lot of them. When the light is very dim, boom, 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 small. These particular boom, booms.
Right. So this is telling us something too. Is that the photomultiplier? I've talked about it before. He's going to describe a little bit of its function, and that'll be fine. Probably don't need to do that part, but we'll just play this through. And what it's telling you, obviously you can set it and it will see photons that we can't see. So it's recognizing a form of energy that seems very similar to what we call a photon, and yet we can't detect it. We can't mechanically see it. So it sort of points out that there's this photon thing can be in a form that's somehow not consistent, in the sense that it can be in forms that we can't see and other devices can, which tells you that they all can't be the same in a way. So even though they all seem like they're the same, it's all the same thing. It's clearly not the same because there's enough of a difference where all of a sudden we're not seeing it.
Bang, bang, bangs and so forth are completely out of proportion. The actual rate is enormous, okay, and a little bit less when there's less light. It's very difficult to get it to a boom, boom, boom. It could so dark in here you wouldn't know what.
So you do have to keep it cool. You have to do lots of things to prevent it from internally just, screwing up. Seeing photons it's making, detecting its own heat. But clearly you can get it so it's not so sensitive that that it's useless.
But this device, to show you an example of how it works, just so you understand, what happens when we detect the weakest possible light is it works like this. There's a metal plate here made of cesium or something. When light shines on it, it knocks an electron out. Then you have another plate here with a voltage that attracts the electron, so the electron, so to speak, falls. It's attracted and speeds up and hits this plate. When it hits this plate, got about 100 volts of energy, it splatters. Other electrons get knocked out of the 2 or 3, 5, perhaps, on the average. Now those are attracted to another plate. And they all go...
So again, attracted, blah, 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 they're actually pushed, but whatever. These are all part of describing any mechanism is getting the push and the pulls right. And it's, this should be where the physicists are a little more humbled than they are in terms of recognizing that they still haven't gotten that part of the drawing right. They still haven't even figured out the simple parts of whether it's a push or it's a pull. And yet they're going to tell us about the gods that exist.
Sailing down here with another 100 volts, 5 of them this time, and each one of those knocks out on the average 5 or 6 other electrons. Now I got 25, and that's attracted to another plate, and that hits those, and so on, and you have a maybe 10.
So the key ingredient is how, obviously it's a cascade, so the key thing is how charged this first differential is. That's the one creating the signal. So the only one that really matters is this first plate and how much charge you have going across it. That's basically going to tell you how sensitive it's going to be, how easy it's going to be to lift an electron. I could put enough charge on it where I could almost pull electrons without even having any other instrumentation effect, without anything else poking it. There would be enough of, what do they call it? The northern lights kind of thing. You got electricity that's in such a subtle form that you can't see it. It's just a little blue glow, where you're leaking the charge in such a small way that you don't see it because it's just not creating any atmospheric disturbance, no spark, but you have a bunch of discharge. And so you can't have it so you're discharging, because any discharge will be amplified. So the idea is to turn it up as sensitive as you can without detecting things that aren't real influences. But yes, you're just making something really, easily disturbed. And so, I have to think of a way to describe that. But, it's like it's the difference between like painting a surface and just putting powder on the surface, where any bit of wind could blow it.
It doesn't plate. By the time you get out the other end, you got such a chunk of charge and electrons, so many of them, you multiply 5 times 5 times 5 times 5, you'll be a long time counting pins to discover how much that is. You get such a tremendous pulse that you can, the number of electrons high enough, you can go directly through circuits and so forth and turn on and off switches and do all kinds of things.
So it's really just an all or nothing, though. It's a clump detector. You have to hit it with enough energy to cause the event, and that's the key part of it. And it has a minimum amount of energy.
Voltages, the pin make noises, do everything. It's amplified. Now what happens when we have a device like this and we put it in the dark is it goes click, 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 click. Every once in a while, a light particle comes in, a photon. This is a particle in every sense. The experiments have all the right properties.
So he says it's a particle in every sense, but it's really not. It's not a solid, indivisible. We haven't, they don't have any evidence that it's a particle. They have every evidence that it's a definable pattern.
As follows: that if you have a very weak light and you have one or two, just one of them every once in a while, If you put two cells out, and there's just a few of them coming, then it goes on one or the other. They don't go off together. They go off together, you got too many coming. You can't.
What he's really pointing out is that it's not like a wave where I can collect it all over the place. I can only collect it in one location at it, it's a clump. It has a defined space that it can travel through.
But if it's very weak, the particle is either here or there. And it comes in particle. I don't know how much I can emphasize this, especially to young students who have learned its waves. It is particles in every way whenever you can detect it. It's unfortunate for us that we can see them.
Yeah, so, so again, I would just argue we're only detecting with a clump detector, but even the clump detector is telling us that there's different photons. There's ones we do see, and there's ones we don't see. The photomultiplier is seeing photons we can't see. It's just a fact. So they have to be in some way different than the ones we do see. And I would argue the difference is probably in this length argument. They're just not, there's not enough wave, there's not enough frequency, there's not enough pattern for an eye to catch it, for some instruments to catch it, but the photomultiplier turned up is catching it. It's catching the broken pieces.
The light, I mean, it's unfortunate for us. No, not quite, not quite. Now if we were 10 times more sensitive to light, then in the dark, we would see that what we're seeing is little flashes, little tiny dips, dots of light. The nerve would...
We'd see that anyway if we just put on dark glasses, theoretically, or some other kind of way of faking the number of photons that come in. But again, there's two parts to this, and I'm not saying there's a resolved answer, but they don't even have the conversation. Oh, I need to switch the camera again. Inconvenient. So there's two ways to look at it. We can only see, say if this was a photon, there's three things at a frequency. You could argue that we only see a photon when three of these show up, right? And hit our eye. And then we say photon, so there's enough of them. Or you could argue that the limiting factor is that we only see the photon if the whole three of them get here. But a photomultiplier can see just two. So it doesn't need as much of a photon to see a photon. It can recognize this as a photon because it doesn't need this. And so there's two ways you could argue about why photons in a certain condition are visible and some in the other condition aren't. Yeah, that's what I want to do. Okay.
Go off, just like the photomultiplier, in spots. But the human eye is not quite that sensitive and takes 5 or 6 of these particles, photons, 5 or 6 photons to make one nerve fiber go off. So it isn't. So we cannot detect with the eye light quite low enough to notice the fact.
So 5 or 6 could be the length, 5 or 6 nodes, or it could be actual 5 or 6 actual photons. Now I don't think it's 5 or 6 actual photons. I tend to think that we have to see more of a pattern, and the photomultiplier can get by on less of a pattern.
Fact that it comes in the form of raindrops. All right? Got that? They're particles, right? And you can detect
See, if there were particles and they were talking about particles, then you would talk about particles at a frequency. And as soon as you say particles at a frequency, then you say, well, you can't tell. If I shoot you with one bullet, you're not going to get any information about how many times I pulled the trigger or how fast I pulled the trigger. It just doesn't say anything. You have to get hit by more than one bullet to know what frequency of bullets you got hit by. So that would be the kind of argument that it appears physics just jumped right over it. It just decided to have some Huygens-Newton argument about wave versus particle in a context where they totally ignored the fact that frequency is one of the fundamental functions of the photon, the frequency. And it's like they just never had a conversation about it.
with an instrument, you can count them, so and so many per second. Bright light, more per second. Dim light, less per second. Okay? Now we start to describe the properties of light a little further. The next property I want to talk about is reflection.
So obviously reflection isn't a property of light. It's a property of the substance you're testing light with. You're letting light hit. So it's a property of the glass or the metal or the thing that you're bouncing the light off of. So this is where, again, I mean, cart before horse, or not even horses. You got, platypuses. Carts and platypuses won't get you anywhere.
From a glass surface or a water surface. I believe everybody knows that you can see the sun or the moon, let's say. In the sea, as it says, reflections are a happy thing in art pictures. There's moonlight reflected from the water. You have a window. When you look through a window, there must be millions of examples. Right back there's one. You look at a window, you can see through it, but also some reflection. Now already there's a problem. Because the light that's reflected is not as intense as the light that's shining. Some of the light goes through the window, say, or through the water down in. Only some of the light comes back. If the light is headed for water, for example, straight down, only about 2% reflects.
So he says 2%, But this is also a surface argument, though, because if in the glass example, you reflect the light off the top surface, and then the second surface reflects the light also. So you get 4%, and but the average is 8%, as I understand it. So, the details weren't very good here. But it doesn't really matter, I suppose. We don't need to know those exact numbers, just that the fact is that you can change the percentage.
What does that mean, only 2% reflect? That means that if we had a photon counter here, let's say, draw the experiment so you know what I'm talking about. It's hard to make a water surface that's vertical. Yes, so we'll make the water surface horizontal. And light's coming down, and some of it's reflected, and we put a counter here to see one of those photo multiplier things, and we count the count. And we know how much we should have got, and we find what. How can it be partly reflected? I forgot to say when I was talking about the particles, when you have light of a definite color, the energy that the first one knocks out is always the same. Each particle is the same strength. There's not half particles. It's a full.
Well, we know that they are half particles in the sense that that there's light we see and light we don't. There's energy in a form that we can't see, but it's recognized by a device as the same kind of energy that we do see.
Photon. What you get is full photon. But if the light is dimmer, what does that mean? There are fewer of them, right? Simple. So, of 100 that come down here, perhaps 4. Now, this way and 96 go through. What determines which 4? How does it, which one that's...
So he's changing it. So it'd be 4 off each surface.
Coming down of the 100 knows what to come back up. All right? So the situation is that the phenomena is probabilistic. It takes odds. It comes down here and has a 4% chance. 1 out of 25 trials. I think you know what odds are. If you have, for instance, a die, and you want to get a...
So again, these odds could be based on the fact of the separation between atoms, the separation between the electrons, what the odds are of hitting an electron versus hitting a nucleus of an atom, and that's all the odds are. So the odds are that yes, you have a 96% chance of hitting an electron before you ever hit a nucleus.
For 1 and you roll it, well, it doesn't come out so often, but it comes out sometimes, 1 out of 6. And what that means, if you roll die 100 times...
So you could argue that the nucleus is compact, and that's the difference, that it's a smaller spatial profile for all of the stuff in the nucleus is in a smaller space, and therefore it's harder to hit the smaller space.
Let's make it 600 times. You roll a die 600 times, you might get 105 1, or maybe 92 1, or something like that, right? You get about 100. And if the numbers were bigger, the accuracy in percentage is bigger, not accurate. So if you have 6 billion, no, not 6, because I got 125, 25 billion of these coming down, about 1 billion will come off. Okay? Now, let's see, if the next feature is how can it be probabilistic? Suppose that I have...
Not how can it be, but why. See, since they're just saying, well, why is it probabilistic? Well, because you have some circumstance that's makes it the two. You can hit different places and they do different things. So that's what probability comes from. Whether just flipping the coin, you can flip it so weakly that you guarantee the outcome, and then you can flip it with enough variables where you can't guarantee the outcome. I mean, it's but the reason why it can be is because it's obviously the surface is creating an environment that has a 1 in 25% chance of affecting that the field has some irregularity in it, like it's all flat and there's one place where there's a dent. There's some mechanism, some cause. He's saying no, there's no cause.
I had a light so weak that I had only one photon coming every few minutes. Will this counter go off, or will the one down here go off? 1 out of 25 times this one goes off. Which time? What determines that? Possible theories. Nothing. Pure chance. The world is made of chance. That would mean that...
So the audience laughed at that, but that's what he's defending. So that's the funny part, is that he's defending that. The throwaway line. Oh, pure chance. It's a joke. He's not joking. That's what he believes.
That the physicists can't predict the future. It would mean that if you set up an experiment with exact conditions, you cannot predict what happens in the future because you can't predict whether it's going to go up or going to go down. You just got 4% odds. Your whole beautiful structure of science is reduced to computing odds. Nature, instead of being definite, does everything by chance. Not so good. Other possibilities are a little...
So he says not so good. But he really means that's the way it is. So that's the funny part. I almost ironic part.
Spots on here. And all the photon has to hit a spot on the surface. And Newton did several things you'll find out.
Right. Newton didn't know what atoms were, didn't know what electrons were, didn't know what protons were. So he could only speculate that the surface that he was looking at was more complicated than what he could see. And so, yes, he could only theorize about some kind of notions. I mean, again, Faraday thought there was a bunch of gears inside of atoms, and the gears were turning, and there's other gears, and, they could only draw the diagrams based on what information they had, and there's perfectly viable and useful speculations, and that's what you have to do. You put a big pile of speculations together, and you see all the different things, and you figure out whether they're viable or inviable, whether they are catastrophically broken or whether they're a little broken, whether there is a problem but it might be fixable, and that's all part of troubleshooting. That's all part of detective work, and I'm just saying that modern physicists have given up, and it's depressing.
Later, when I give you more phenomena, how these various explanations, which way it's going to go, and why the spot one doesn't work. But I'll give an argument that Newton made about that. He said it can't be that, because, he said, you can polish glass. It's wonderful. I love to read these old guys. They knew you could polish glass, but they had the intelligence to deduce from the fact that you can polish glass that there's no spots on it, like why. What's polishing? See, he polished...
Yeah, I know, but that still doesn't tell you anything except that Newton knew that what does polishing mean? Well, it's changing the distance between the top layer and the bottom layer. And so it might be a reason to believe that maybe there's something about those layers that are changing what the surface looks like. So if you did think it was made out of little blobs, you could say, well, if I'm knocking some of the blobs off, I'm changing which ones are high and which ones are low and how they would fit together. And you could understand that, yes, of course, the two surfaces are communicating in the sense that if I rearrange a row, if I change where the position of this atom is, I'm going to change the one below it and the one below it and the one below it and the one below it. So if they were made out of hard steel balls, you could understand if you were rearranging the surface, one surface, you have to rearrange the bottom surface. There's no way around it. If they were hard steel balls, there's no way around the fact that if I screw up the top surface, I'm screwing up the bottom surface. But the spots wouldn't go away. You're just changing where they are.
He carved his own lenses. He ground his own lenses. So he knew what it was doing. He takes a coarse-grained sand-like stuff for, what do they call it, the polishing powder, the grinding powder, and that shapes it. But it cuts fairly obvious grooves. And you take a finer one with finer particles, and you cut the grooves are finer, and you make the grooves finer and finer and finer. And after they're fine enough, suddenly it's smooth and the light comes right through. When it's coarse, it's bounced around. And so he concluded that light cannot see the grooves. That when I polish it, it's not that it's smooth. It's still bumpy, but on a small scale. Whereas when I dump the big grains, it's on a big scale. It can't be any different. When I polish with the small grains, it's just a small scale of regularity. But somehow light doesn't see anything on a small scale. Correct.
See, the fact is, though, it does see it. So the more scratches I have in the glass, the more I diffract the light. And so the light goes in all kinds of directions. It scatters all over the place. So it clearly creates a huge effect. So I don't know exactly what... I mean, obviously, they're not spots like surface irregularities or some kind of dirt, because, yes, it still exists when you polish glass and change its thickness. But you are changing how much the light reflects by changing the thickness of the glass. That's what Newton found out. So I don't know about, like I said, the spot argument doesn't say much. But the fact that how much light reflects changes based on how thick the glass is, that says a lot. It certainly says that why would I think it has something to do with randomness? It's clearly not random anymore. I mean, I'm changing fundamentally what the odds are by physically changing the glass. Isn't it kind of obvious that the property affecting the light is in the glass and it's not in the light?
All experiments have shown that this is absolutely not the right explanation. If it was, there'd be all kinds of ways of testing that. I told you we can measure down to 10 to the minus 15 centimeters and so forth. And what would happen would be you'd be able to find some area to focus very carefully the light so that the reflection coefficient would be...
I mean, obviously we can't do that on an atomic scale. So he's talking about the fact that we can measure down to blah, 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 blah. Well, it doesn't matter what you can measure down to. You clearly can't measure down to a single atom and watch a single atom react to a single photon. So that you can't do. Not even close. I mean, you're like miles and miles away from that. So, and that would where the spots would be on the scale of the photon. So, again, fail. Little tiny spots, you still can't get rid of that theory.
Higher than 1 in 25 because you happen to be near a place where there was a spot. Can't do it. No matter what you do, it's 1 in 25. Other possibility, the light that's coming down here, the photons are doing, like footballs. And they spin. And depending upon whether they hit with the nose...
So again, I don't know why they would even start talking about what photons are doing when clearly it's what you've done to the surface that's changing what the photons are doing. You're changing what kind of shoes the players are wearing. And when they're kicking the ball, you're not changing the ball.
Point or with the flat point depends on whether they bounce back. In other words, something inside the photon is determining which way it goes. Again, no. Because if that were the case, the light that went through would be all of a certain kind of football. And if you try the reflection again, you'd expect a different number than 4% because of the fact that they're all lined up, and you can't line light up. You can't.
So, obviously, there's tests to see if certain theories make any sense, and whether you change the photons or not could be deduced, like he said, by filtering it and figuring out that you don't get any reflection once you've reflected them once, and that will tell you something. But all these things are telling you this isn't about what photons are doing, it's about what the surface is doing. And I don't know why that's never the conversation. So it's just another example that, when they do the double slit, they do this, they never pay attention to surfaces. They just keep trying to make photons do it. Like it doesn't happen to photons, that somehow the photons are happening to the surface.
You can't fiddle around up here by any kind of filtering that'll change that percentage. All the lights, photons, are identical if they're the same color, in one color. They're all identical, and they behave with 4%. Are we therefore reduced to this horror that physics has got reduced not to these wonderful predictions, but to probabilities? Yes, we have. That's the situation today.
So right, so he's just arguing that we gave up and we've decided it's magic and that's it and no further. All right, continuing and such.
In spite of the fact that philosophers have said it is a necessary requirement for science that setting up an experiment exactly similar will produce results exactly the same the second time. Not at all.
All right, so we saw that exact line in the videos he did 15 years earlier. Pompous, statement that it's kind of silly for us to expect that that's how the universe works. That's cause-effect universe, a mechanical universe. So he's completely arguing against any of that, and in my opinion, that's just a religious statement because there is really no hard evidence. They haven't broken the idea of a cause at all here. He hasn't proven that there's no theory of how the glass is mechanically arranged to explain why reflective indexes change. Nothing. They have nothing to base this surrender to except their own arrogance. You know, he's just saying, well, I've been around a while. I'm whatever he is here, 50, and I've given up on trying to figure it out. That's it. And because I can't figure it out, you can't figure it out, nobody will ever figure it out, so therefore let's all just give up and we'll just pretend the universe is magic.
1 out of 25, it goes up and sometimes it goes down. Unpredictable, completely by chance.
You just said it, though. It doesn't matter. If I really can create identical circumstances where the photon travels the identical path and the matter's in the identical condition, he's saying overtly to you that it doesn't matter whether the photon goes in the middle of the slit, it doesn't matter whether the photon goes on the edge of the slit, it doesn't matter where the photon goes in, doesn't matter what happens in terms of how much I vary that circumstance, I'm always, the random God's going to dictate the outcome. Not location, not position, not where it hits, not a mechanical cause, a wooey magic universe where if I make the slit big enough, I can make entire galaxies, random or something. It's silly, it doesn't work, it doesn't make any sense. If you analyze that theory, it falls apart because it creates paradoxes and nonsensical notions of function.
All right, I really see you turning off. I can see you say you don't understand.
I wish people just say, no, I do understand. I understand we already been down this stupid religious road. I thought we figured out that making shit up and surrendering and giving up and not pursuing, not working a little harder to find out the details and to get the right answers, that all of that stuff is the good way of doing it. And it's really the sucky, stupid way is for, the Europeans to show up with shiny beads and flashy mirrors and for me to fall for it, for me to think there's magic.
You can't understand that it could be chance. I don't like it. Tough.
So there's the I don't like it tough remark. He earlier said too bad or whatever, and so it's 3 times he's pointed this out or iterated this line. You don't like it tough.
I don't like it either, but that's the way it is.
I don't like it either. Yeah, well, you don't unlike it enough. Okay, that's for sure. To settle for it is just giving up, surrendering, just saying science doesn't work. It's just a nonsense, and there's no good reason for it. Just no good reason. You don't have nearly enough evidence that it's unexplainable. You're not even close to have done enough work to say it's unexplainable, because theoretically, I've said this before. I mean, obviously, all of this science got put together in some sort of, there was no order. It wasn't like this was a well-planned assembly line. The whole thing got cobbled together with little events in history and little people doing little experiments. And, they never even, they didn't really, Volta made a few equations that were complete horseshit and everybody accepted them. Different things happened where, it was garbage. They just said, oh, it's an R cubed rule or some other, and it really wasn't. And so all that kind of crap happened. Benjamin Franklin gets plus and minus wrong. So what? So it's all little pieces of little bits of innovation, but there's been no precise obligation to really examine anything. And so I made this point. I mean, the Young experiment was wrong, and they could have known it was wrong even back in Young's day. I mean, the 2-wave thing doesn't work. The pattern is in the wrong place. If I make the slits any kind of width opened, a few hundred wavelengths of opening, the math for 2 waves completely fails. So I mean, it's like they could know it then, and they certainly knew it by Feynman's time. They could have known it, but they just didn't care to get into the details.
Hey, I don't understand it either. I don't understand it. It must be that nature knows whether it's going to go up or down. No,
Nature knows. I mean, even this rhetoric is just so, ugh. It must be that there's causes and effects. And, again, here we're supposed to believe that the entire universe functions based on this rule that we can see what causes things. We can see the asteroid hit the moon and cause the crater. So, I mean, we can see the causes, we can see the effects. It's just there's a clear connection between them. And the only place where we're going to break that rule is the place that's so small we can't see what's going on. And that's the place where all the magic is. Now, isn't that just too convenient? I mean, isn't that just obvious reason to be incredibly skeptical of their conclusion that it's time to give up? It's time to give up on cause and effect because, our microscope is 4 million times too inadequate for us to see anything. And, but it tells us that we can't do it. We can't figure it out. I mean, it's just stupid.
It does not be that nature knows. We are not to tell nature what she's got to be. That's what.
Oh, so again, this, who's trying to do that? You're doing that, and just like I said, to give up is just to say you're telling us, what it's to be, because you're forcing us to bail on the question way too soon. And it's just the same fault of the religious people, right? I don't want to be bothered with the details. I won't go looking for the correct answer. I'm just going to accept this silly one.
We found out. Every time we take a guess at how she's got to be and go and measure, she's clever. She's always got better imagination than we have, and she finds a cleverer way to do it than we have thought of. And
There's nuance to everything, and everything there's little catches to it, and there's little, if you don't have the governor on the motor, the motor just runs itself into disaster. And so you need that little catch, that little mechanism to prevent the motor from just going crazy, just revving up until it breaks. Little subtle things that make things work. And so you have a theory and you can construct most of it. You get an 80% of it or 70% of the mechanism, and you sort of get the idea of what it's doing. Yeah, and the other 30% is still broken, still not quite right. It's still little problems. But they're there to be solved. Just like understanding evolution, and understanding these subtle differences. It's a huge difference, right? Thinking about evolution with a giant herds evolving over time, and changing the way they look a little bit at a time or something. And then understanding how, no, that's so much more possible in a little tiny population. It's a subtlety, but it's just critical to understanding the actual mechanism and making it actually work. And then it explains things like, well, why there's no, missing links, and why this and why that. I mean, it fits. And then it answers a whole bunch of more questions. They gave up on all that whole process so they could do math equations.
in this particular case, the clever way to do it is by probability, by odds. And so
the clever way to do it. No, the way to just ignore trying to understand why it happens and all the value you might get out of that understanding, and instead just get to the end, okay? All we want to know is consequences. We don't want to know causes. We're abolishing cause is significant, and it's just really, really bad science.
Aspect I have to tell you about then is that light works by probability.
So again, yes, of course, there's probability involved in all interactions. I mean, there's just no interaction can be perfectly the same. There's no circumstance that could ever be perfectly the same except some artificial one you create in your imagination. In terms of trying to see it as, it can be essentially the same, but it can never be the same. But it's no point. No. I mean, but there's every indication that all it has to do is fit the conditions.
All right. By the way, just incidentally, the wave theory had no difficulty with this at all, because what happened would be like the waves of something are coming down here, and they shake and they just keep going, but some of them bounce back. Something like a sandbar sometimes partially reflects the waves in the sea, so some of the energy went back. But waves don't.
Again, it still doesn't. I could find just as many flaws in that argument, in terms of, well, that's nothing but a little spot argument too. I mean, the waves have to be mechanically, something has to be causing the waves to reflect. So what's the mechanical mechanism? You're still stuck with describing the mechanical mechanism. But here he's going to say it again. He doesn't think light is a wave.
Operate this thing. By the way, when you turn the light on, this might go off at any moment. You don't have to wait for a certain length of time. Of course, there's odds that it goes off at any instant, but it could accidentally go off the moment you open the slit. So it's not a question of waiting for the energy of the wave to pile up or anything. It's hopeless.
It's not waiting for the energy to pile up. Well, who would think that waves have to pile up? But again, you do have to wait for the whatever the cause is to take place. So, there's an event. It's going to be an event that happens in a trillionth of a second, but it's still an event that has a process. The electron moves from point A to point B, and something is moving it from point A to point B.
I have to start with light as particles. Waves explain many things, but not light. It's particles, okay? Okay. It's photons. The problem is they're reflected with probability.
All right, so again, he says they're photons, but they're not photons in the sense that they are a composite object. They're a pattern. That should be something reasonable people can recognize, that we're really talking about a pattern traveling through space.
Now, the next feature, having to do with reflection again, that I would like to describe is something that you're also familiar with, perhaps not so directly, but perhaps you've seen the colors in soap bubbles. It's made out of soap water, which has no color. No color, I've seen the color. Mix it together, get a lot of soap water together, and look at it. No color. You take...
All right, so I'll pause or stop here. Maybe we'll do some more of this, but we've already been through some of the experiments he cites, and they're good experiments to cite. They show phenomenon, all that kind of stuff, but again, they're not properties of light. They're properties of the mediums you expose light to. So they're not telling you directly what a photon is, they're telling you indirectly. And we already can, again, knowing some of that stuff, but when you sit there and describe what a photon is, what these experiments are telling you a photon is, it's telling you it's way too big an object, a thing in space, to be created by a single electron moving somewhere. There has to be more activity than that. One single electron doing one single little event will not create anything that we can describe as a photon. There has to be more of it happening at one time than just one. And that would explain also why we can't create single photons, and why what we assume to be isn't necessarily what actually is. That if you're receiving a single photon, there was probably more than one photon involved in the creation of that photon. All right, anyway. Yeah. So, till the next time and such and blah, 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 I guess. Just depressing. As stated, it's depressing how few people are interested in some sort of sensible analysis of what we have as a knowledge base in terms of figuring out where we are and what's going on. Awful lot of people who have just chosen a notion, and most of the notions have something to do with Smurfs and pixies instead of anything real. It's all people still living in a world of leprechauns and other figments of their deluded, immature imaginations. Anyway. Shit. I hate this planet. It sucks. It's really hard to have an intelligent conversation here. Yeek. So, till the next time, such. more than one.